Hello, welcome to lecture 10 of this course. In this lecture, we will learn how to deal with the quantum state of a composite system. This will lead us to the concept of the reduced density matrix. So, let us begin. In general, we do not consider a single quantum system, rather a set of systems, mostly a composite system. Say we have two systems A and B. Okay, and system A lives in the Hilbert space HA and system B lives in the Hilbert space HB. Then together we can say that both A and B live in the Hilbert space H is equal to HA tensor product HB, and this is the symbol for tensor product, and it is also called direct product sometimes. It is called tensor product or direct product. Let me repeat once again. So we are considering two systems A and B. They are now the composite system. System A, if I consider it alone, it lives in the Hilbert space HA, and the system B lives in the Hilbert space HB. Together, if I consider both A and B, I can construct a common Hilbert space H is equal to HA direct product or tensor product HB. Okay, so now let us say HA, the Hilbert space of A, HA is spanned by the basis vector, spanned by the basis phi. Okay, phi I, and HB is similarly spanned by another basis state by the basis say psi j. All right, so I and j can run from 1 to n if it is a n by n dimensional Hilbert space and so on. Then we can construct a basis state for the common Hilbert space, and this basis state is going to be phi I, which is the basis state corresponding to the Hilbert space of the system A, and psi j, which is the basis states corresponding to the Hilbert space of the system B. Then together phi I direct product or the tensor product psi j is the basis state these are the basis states in the product Hilbert space H. Okay, so this is the way we describe a composite system in a product Hilbert space, and this would be more clear if we'll do some examples also. Now let's say if A and B are linear operators, say A and B are linear operators, and these linear operators corresponding to some physical observable. A correspond to a linear operator in the Hilbert space HA, and B is the linear operator corresponding to some observable corresponding to the system B in the Hilbert space HB. Okay, then in the composite Hilbert space or the product Hilbert space, we can define an operator A tensor product B. So this is going to be the operator in the Hilbert space H, and H is the Hilbert space. It's a product Hilbert space constitute due to the Hilbert space of corresponding to the system A, and HB the Hilbert space corresponding to the system B. Now when this operator, composite operator AB, operates on, it's going to operate on the basis state of the product Hilbert space. So say for example, the basis state corresponding to system A is phi A, and the basis state corresponding to system B is say psi B. Then if this operator A tensor product B operates on it, then quite clearly A is going to operate only on the basis state phi A, and B is going to operate on the basis state psi B. Okay, so in fact, we can extend this idea or concept to more than two systems. Now, as you know, operators can be represented by matrices, and this helps us to define the tensor product operation of two operators. Now, let me explain how to do that. The tensor product, as I have already told you, it is also called the direct product of two matrices. Say I have this matrix A, it has a dimension say m by n, that means m rows and columns, and B is the matrix having dimension, let us say it also has the dimensions, it may be any dimension, let us say any dimension, okay, it may be m by n or any n by n or whatever be its dimension. Then I can define the tensor product of these matrices A and B as follows. A and B would be, let me first write down the matrix for A. A would be A11, A12, like this. It will go up to A 1 here, and n columns are there. And then if I go by the rows here, the final row is going to be m, and am1, am2, okay, like this. The last element is going to be m rows and n columns, like this. So this is the matrix for A and tensor product with B. And now how it is defined? So what you have to do, just multiply each element in the matrices by the matrix B here. Each element is multiplied by matrix B, say A11B, A12B, A1NB, okay, and similarly AM1B, AM2B, and final element AMNB, and so on. Okay, now let us actually do some examples to understand it further. Say example, for example, let us find out tensor product. Find tensor product or direct product, tensor product of K0 and K0. Okay, that means 0 tensor product 0. In fact, this is written in the short form as simply 0, 0. Okay. Now you know, let us do it. You know the matrix representation of K0, that is just a column vector. You have 1, 0, and therefore K0 direct product with K0 is going to be 1, 0, direct product or tensor product 1, 0, and you know this guy is going to be multiplied with 1, and then it is again going to be multiplied with 0. So therefore, let me explain here. You are going to have 1 into this one, so it would be 1, 0, and then 0 into 0, so this would be 0, 0. So this is going to be your tensor product. Similarly, I can go it with say tensor product of 0 and 1, which is basically K0 tensor product with K1. Now you know K0 is represented by this column vector 1, 0, and K1 is represented by the column vector 0, 1. So you can easily see that 1 is going to be multiplied with 0, 1, so it would be simply 0, 1, and 0 is going to be multiplied with 0, 1, so this is going to be 0, 0. So this is the tensor product or direct product of K0 and K1. Now let us do another example. Say find the tensor product of sigma x, the Pauli vector sigma x, x component of the Pauli vector, and y component of the Pauli vector sigma y. Okay, so how to do that? You know the matrix representation of sigma x. Sigma x is equal to 0, 1, 1, 0, and sigma y is equal to 0 minus I 0. Okay, so sigma x direct product or tensor product with sigma y would be 0, 1, 1, 0, direct product or the tensor product 0 minus I 0. Now this 0 is going to be multiplied by sigma y, 1 is going to be multiplied by sigma y, similarly 1, this is going to be multiplied by sigma y, similarly 0 is going to be multiplied by sigma y. So you can easily see that what I am going to get is, you are going to get a matrix that is going to be a 4 by 4 matrix, and this is going to be, it is multiplied by 0, so 0 0 0, here it is 1 is there, so it would be 0 minus I 0, and again you will have 0 minus I 0, and finally you are going to have 0 0 0 0. So this is the tensor product of sigma x and sigma y. I hope you get the idea. Now let us suppose that we have a composite system A plus B, but say we are interested only in system A. We are interested only in system A, not in B. Okay, we are interested in system A only. Then the question is how to extract properties of system A from the composite system A plus B. This can be done by a prescription known as the reduced density matrix. Reduced density matrix. And let me explain that. The composite system, this composite system A plus B, its state, quantum state, can be represented by the density operator or the density matrix rho AB. Now, as I said, we are interested only in system A. We want to know the density operator corresponding to system A only. So how to do that? Because we are given the information about the density operator corresponding to the composite system A plus B only, that is, we know rho AB. Now from here we have to find out what is rho A, the density operator or the density matrix corresponding to system A. This can be done by tracing out the system B, tracing out the system B from rho AB. Okay, and let me explain how this can be done. Let us say we have this density matrix rho AB, and it is given by in this form, say A1 A2 ket A1 bra A2, and this part corresponding to system A, tensor product with ket B1 bra B2, this part corresponding to system B, and this part corresponding to system A. And by tracing out B means, what we will do, we will just take the trace over rho AB. That means rho AB is given as ket A1, ket A2, tensor product or direct product, ket B1 bra B2. And when we are taking the trace, we are going to take the trace over system B only. So we will have ket A1, ket bra A2 as it is, and then trace operation is going to be carried out over ket B1, ket B2, which is corresponding to system B. Alright, now say we have this phi I, ket phi I are the basis in the Hilbert space of B. Okay, then trace of ket B1 bra B2, I can now work it out as it is. So I have to take the trace with respect to the basis state phi I, because phi I are the basis state corresponding to the Hilbert space describing the system B. So I have here phi I, then I have here for the system B I have ket B1 bra B2, then I have here phi I, and as you can see these are just numbers, so I can take it this I can take it to the other side, and I can take it to this side. So if I do that, what I'm going to get is this. I have sum over I B2 ket phi I, and this is phi I b1. Now if you apply the so-called orthonormality completeness condition, in fact, so you know that sum over I ket phi I bra phi I is identity. So as you can see, this is identity, so we'll be left out with only bra b2 bra b1, which is just a number, it's a scalar product. So then what we have, so we have trace b, when we have taken trace over row AB, that is A1, A2, tensor product B1, B2. So we will have simply this number B2, B1, and we have this ket A1, ket A2, which is just an operator, and this is the density operator corresponding to the system A. So this is how we can find out the density operator of a system from a composite one. And similarly, suppose you want to find out suppose you are interested only in system B, then you have to trace out A from row AB, and this is going to give you the density operator corresponding to the system B. So let us do some example to understand this tracing out procedure. So let me do the first example. Let's say we have a 2-qubit system described by this quantum state says ket psi plus, and this 2-qubit quantum system is tensor product 0 0 plus 1 1 by root 2. Let me elaborate it further. What I mean by this is I have ket 0 tensor product ket 0 plus ket 1 tensor product ket 1 divided by root 2. Now here this one first ket 0 represents the first qubit, and the second one is the second qubit correspond to second qubit. This first ket 1 correspond to the first qubit or the first system, and the second one correspond to the second qubit. Okay, this is the convention. So to find out, suppose now we are interested in the first qubit only, so I have to trace out the second qubit, but before I do that, first I have to find out the density operator corresponding to this ket psi plus. So density operator, let me quickly work it out. That would be ket psi plus by bra psi plus, and if I do that, what I'm going to get 1 by root 2, 1 by root 2 is going to give me 0 1 half, and I have here 0 0 plus 1 1 from this ket psi plus, and from bra psi plus I have bra 0 0 plus bra 1 1. Okay, now let me open it up. If I open it up, then I am going to have 1 half, I have ket 0 0 bra 0 0, right, ket 0 0 bra 1 1 plus ket 1 1 bra 0 0. It's very easy to follow these calculations. Ket 1 1 bra 1 1. Now here again, remember that this first one element represents the first qubit, second one represents the second system or the second qubit, and so on. Here it is first, here it represents second, and so on. Okay, so now if we are interested, as I said, in the first qubit only, then we need to trace out the second qubit, and this is going to give us the density operator for the first qubit, and therefore let us trace out the second qubit. So to take the trace out of the second qubit, I have to do the trace operation on the second system or the second qubit, and this is going to give me the density operator for the first qubit. So I have row 1 is equal to trace operation I'm going to do over row on the second system. So as we have already seen this prescription here, you see this one, just let us apply. So let me explain. So I have my row as this is my row, and first qubit is going to remain unaffected. So let me take out the first qubit. This is first qubit, and then I have to take the trace operation on the second one. So that is this one, 0 ket 0 bra 0. Okay, Similarly, I'm going to do it for all the other elements. So let me do it. You can easily follow, I hope. 0 1, this is the first qubit corresponding to the first system, and trace operation I have to do it on the second qubit here. And similarly, from the third element I have gate 1 bra 0, trace operation over gate 1 bra 0. Okay, and the last element gate 1 bra 1, this is corresponding first system or the first qubit, and I have trace 1 bra 1, that's correspond to the second qubit. Now you know this trace operation is simply going to give me the scalar product 0 0, which is equal to 1. This is going to give me scalar product 0 1, this is going to give me 0 because gate 0 and gate 1 are orthogonal to each other. Similarly here, this is going to give me 0 1. Okay, this is also orthogonal, so this is going to give me the number 0, and here I have the scalar product 1 1, and this is going to give me 1. So I am just going to have only two non-zero elements there, so therefore I have rho 1 is equal to 1 half gate 0 bra 0 plus the last element gate 1 bra 1. Okay, so this is the density matrix corresponding to the first system or the first qubit, and which we have worked out by using the tracing operation, and we have taken the trace operation over the system second qubit, and this rho 1 is known as the reduced density matrix corresponding to the first qubit. Similarly, you can work out the second qubit if you are interested in knowing only the second qubit, or you are interested in working on the second qubit only, then you have to do the trace out the first qubit, and that you can do by taking the trace operation over the first qubit system. And if you do that, then again you can check, you should get 1 half the same answer you are going to get here, gate 0 bra 0 plus gate 1 bra 1. As an another example, let us consider a 2-qubit system again. This time say it is represented by the state vector gate psi is equal to 1 by root 2 gate 0 1 minus gate 1 0. Let me again remind you that this first qubit, first one here, this 0 belongs to the first qubit or the first system, and 1 represents this one, the second one belong to the second system or the second qubit. Similarly here, this belong to the first qubit, this belong to the second qubit. Now let's say we are interested only in the second qubit or the second system, then we have to trace out the first qubit, but before that we have to find out the density operator for this composite system, which should be rho is equal to gate psi bra psi. So let us follow this procedure. Gate psi is equal to 1 by root 2, you have gate 0 1 minus gate 1 0, and then bra psi is 1 by root 2, you have bra 0 1 minus bra 1 0. Let me now open it up. If I open it up, I will get 1 half here, and then inside I will have gate 0 1 bra 0 1 minus gate 0 1 bra 1 0 minus these calculations are very easy to follow. I hope you are following it. Gate 1 0 bra 0 1, and then finally I have gate 1 0 bra 1 0. Okay, so this is the density operator for the composite system. So if we are interested in the second qubit or the second system, so I have to trace out the first qubit. So tracing out first qubit from rho, I just have to do, we have already done it, the procedure is as follows once again. So you will take the trace over the first qubit. So you have 1 half here, trace for the first qubit, you in the first term you will have gate 0, as you can see, the first qubit gate 0 bra 0, and the second qubit is gate 1 bra 1 here, and then in the second term you have trace, you will have gate 0 bra 1, and here for the second qubit you have gate 1 bra 0, and for the third term you will have trace kth1 bra 0. Okay, and second qubit you are going to get kth0 bra 1, and finally the last term, from the last term you have trace over kth1 bra 1 and kth0 bra 0. So already we know that if I take trace, this term is going to give me the scalar product 0 0, which is simply equal to 1 because kth0 is normalized to itself, and this one is going to give me the scalar product 1 0 because kth0 and kth1 are orthogonal. This is going to give me 0. Similarly here, this is going to give me the scalar product 0 1, that is again going to be equal to 0, and finally this one is going to give me the scalar product 1 1, this is going to be equal to 1, and this will give me the density operator for the second qubit as rho 2 is equal to 1 half. I will have kth1 bra 1 plus kth0 bra 0. Okay, now let me quickly tell you how to express the density operator in the matrix form for a composite system. You already know how to write the density matrix for a single system. So let me once again write the density operator for the composite system that we have considered previously. Say rho is equal to 1 half kth0 0 bra 0 0 plus kth0 0 bra 1 1 plus kth1 1 bra 0 0 plus kth1 1 bra 1 1. So this is a density operator for a composite system. Now the trick to write this in the matrix form is as follows. So what I will do, I will arrange my rows and columns in such a way. So let us say here I put 0 0 0 1 1 0 1 1 as row, and here 0 0 0 1 1 0 1 1 as my column. Now you just pick up the terms. So say 0 0 kth0 bra 0, here you have kth0, then bra 0 is here, its coefficient is half, right? So therefore I will have simply half here, and similarly again you see kth0 and kth0 as row and 1 1 as column. If you think it this way, kth0 0 as my row and 1 1 as column, so this will belong to this spot, and this is again 1 half here, its coefficient is 1 half. And again if I look at this third term here, row is 1 1, so let us have this term spot, and 0 0 is again 0 0 is my column, so this again would be 1 half, its coefficient is half. And finally 1 1 1 1, so this is row is 1 here, okay, this one, and then you see the last, so here it will be half, and all other terms it's going to be 0, its coefficients for all others are going to be 0, so you simply put 0 0 0 here. Okay, so this is going to be the matrix, or I can also write it as 1 half. I have 1 0 0 1 0 0 0 0 0 0 0 0 here, and then finally the last row 1 0 0 1. Okay, so this is going to be the density matrix of the composite system. Okay, by the way, what about the matrix representation of the first qubit? We have already worked out this problem. So in the case of the this particular problem, we have to trace out second qubit, and we worked out that the density operator is 1 half. You have kth0 bra 0 plus kth1 bra 1. Okay, so to write it the corresponding density matrix, so again the trick is here, because this is a single system now. So here the trick is you arrange it in the row as 0 1 here and column as 0 1, and then you just take the coefficient. So 1 half is common, so here you have 1 and here you have 1, and then this is the density matrix representation for this single qubit system, right? Okay, to clarify this thing further, let me consider another example. This time let me consider a composite system given by this state vector. Say k psi is equal to square root of 2/3 0 0 plus 1 by root 3. It should be root 3 because then only it will be normalized the whole system. 1 by root 3 1 1. Okay, now let us write down the density operator for this composite system. So to that you just have to take k psi bra psi. Please do that and you will get it simply as, if I open it up, I will get 2 by, okay, let me actually do it. 2 by root 3 here is k0 0 plus 1 by root 3 k to 1 1, that's from k psi, and for the bra psi I have 2 by root 3 square root bra 0 0 plus 1 by root 3 bra 1 1, and if I open it up then I am going to get terms like this: 2/3 0 0 0 0 plus root 2, it would be root 2 by 3 0 0 1 1, and I will have root 2. This would be third term is going to give me again root 2 by 3. Okay, this would be 1 1 0 0, and the final term would be 1 by 3 1 1 1 1. Okay, now you just note down the coefficients. So therefore I am going to have the density matrix would be as follows. Again, you just arrange the rows as this: 0 0 0 1 1 0 1 1, and here in the column you have 0 0 0 1 1 0 1 1. And now if I note down the coefficients, then you have 0 0. For this it would be basically placed here, 2/3 here, and 0 0 1 1, this one would be, it would be 0 0 1 1, so this would be sitting here in the last here, 2/3, and then again you have 1 1 0 0 1 1 0 0, this would be root 2 by 3, and finally this one is going to be 1/3 here, and all the other elements are going to be simply 0. Okay, so this is how you can represent the density operator in the matrix form even for a composite system, and you can extend it to higher qubits as well. Let me stop here for today. Now we are equipped with some important tools of quantum optics. This will help us to explore many things in quantum optics. As a first exploration, we are going to understand some basics of quantum computation in the next lecture. So see you in the next lecture. Thank you.